All right, so exam 3 is on Tuesday. I guess that is the 4, 5, 6, 7, 327. And the topics are everything up through structures. And so I was just planning to spend today just answering homework questions that you have, and then when you're done with that, I'll just give centroid and structures problems to help you get ready for the test. So first, anybody have any homework questions? Yes. Okay, do you have it with you? I didn't bring that. Okay, so number 2. I thought I was going to make this look so nice. Oh, well. Okay, so there's that. And then there's that. That's not so bad. And another pin joint over here. And these two are connected by a pin joint. The angle with the horizontal of each of these is 10 degrees. There's a 6,000 Newton force applied at this pin. I'll number them 1 and 2, and the joints I'll call this A, B, and C. And the mass of 1 is equal to the mass of 2, and that's 50 kilograms. And we want to calculate the external loads on each member. Bless you. So first I'm going to isolate member 1. There's a weight force at the center of 50 times 9.81, so 490.5. At the left end, there's a reaction force vector. That's a pin joint, so we know that's a force vector. I'll call that RA. And now at the pin joint at the right side, we have to think about, this is where we have to be a little bit careful. I am going to assume that the joint itself, the pin itself, is part of the lowest numbered member. So that pin I'm gonna treat like it's part of member 1. And that means that 6,000 Newton force is applied to member 1. And then that pin that's part of member 1 is in contact with member 2. So there's also this force vector F12. The lengths are, I didn't give that, but that's given. The length of 1 is equal to the length of 2, and it's 1 meter. Okay, so force, moment. I'll start with RA. And for an about point, I don't know, you can make a good argument for the other side being easier, but I'm just going to put it here. So that force RA has a row vector of 0. The force is RAX, RAY, and the cross product 0. And then next is the weight force. Row vector is 0.5 because the distance is 0.5 from the about point to that force. And the angle is negative 10 degrees. So that's 0.5 times cosine of negative 10, which is 0.4925, I think, 0.493. And then 0.174 divided by 2 is 0.0867. Negative 0.087. The weight force is 0, negative 490.5. And what's that cross product? 0.493 times negative 490.5. Negative 241.82. And then the force F12, the row vector is 0.985, negative 0.174. The force vector is F12x, F12y. So the cross product is 0.985 F12y plus 0.174 F12x. And then the last force is the 6,000 newtons. It's the same row vector because that's at the same spot. The force vector is 0, negative 6,000. So what's 0.985 times 6,000? Negative 5,910. So Newton's second law, you can write out those equations. I'm going to just go right to the equation form for the system of equations. So equation 1 says RAX plus F12x is equal to 0. Equation 2 says RAY plus F12y is equal to positive 6,490.5. And equation 3 says 0.174 F12x plus 0.985 F12y is equal to 1 So 6, 151.82, is that right? And then the free body diagram for member 2. We have the weight force at the middle. That's 490.5. We have the force vector RC at the pin on the right. And then at the left end, that 6,000 Newton force isn't applied to this one because it's applied to the pin, and the pin's part of the other member. But this member is making contact with the first one, so there's a force onto by 1, and I'm going to write that as negative F12 using Newton's third law. I'll use this as the about point for this body. So rho, force, moment. First, the force negative F12. The rho vector is 0. The force vector is negative F12x, negative F12y. Cross product is 0. Then the weight force is at 0.493, positive 0.087. The force vector is 0, negative 490.5. And that cross product is negative 241.82. And then the force RC, the rho vector is 0.985, 0.174. The force is RCX, RCY. Cross product is 0.985 RCY minus 0.174 RCX. And so our equation 4 says negative F12x plus RCX is equal to 0. Equation 5 says negative F12y plus RCY is equal to positive 490.5. And equation 6 says negative 0.174 RCX plus 0.985 RCY is equal to positive 241.82. So now we have 6 equations. I think we should have 6 variables. We have the force vector RA, so that's 2 variables. The force vector F12 is 2 more, and RC is 2 more. So now we have a system that we can solve. Anybody want to go through the calculation from there? Is that system of equations good for everybody? Okay. Any other homework questions? Yep. Mm-hmm. Maybe that was sort of in my head. Maybe I'll assign a handful more, and the whatever problems are on the test will just be of that type, you know. So say I assign 5 more or something, then you'll just be responsible for the stuff that comes up in those first 7. I think that sounds reasonable. Okay. Any other homework questions anybody wants to see? Otherwise, I'll just come up with some, or maybe we could even do one of these homework questions that I haven't assigned together. All right, well, let me go to number 5. And what I want you to do on this is, so here's what it looks like. It's sort of, there's a lot going on. So there's a beam like that, and a pin joint there, and a pin joint at the midpoint. And all of these joints are pin joints. And let's say that this distance is 0.5 meters. This distance is 1 meter. These angles are both 20 degrees. And then there is a distributed load here. Where this has a maximum of 1,500 newtons per meter. Okay, so first, let's do this with the numbering 1, 2, 3, 4, 5. Okay, and first I want you to just go through and do the free body diagrams for each one of those members. We're not going to do any calculations right now. So with this numbering, draw a free body diagram for each member. Okay, we're ignoring the weights of the individual members. Okay, so go ahead and work together. Ask me questions if you get stuck. Compare your answers to each other, and then I'll go up and talk through it. And then we'll renumber it and go through the same thing again. Just because really, you know, I think a lot of people think of this as a part that, like, this might be the part that people gloss over the most, but this is really the key to getting these problems right more than anything else. The rest of the stuff is all stuff you've already done. So you don't have to do this on every problem, but sometimes if you get confused, and you know, the joints where you have more than 2 members at them are usually the trickiest ones. Drawing a side view of what's happening can be a really helpful thing. So let me just draw like what's happening at the side views of each one of these joints before I start the free body diagrams. So at the joint A, we have the member 1 going away from us and member 2 up, and then the pin going through them both. And we're going to lump the pin in with member 1. And so, you know, anything that's happening to the pin, if there are external forces applied or anything like that, they're applied to member 1. And then member 2 touches member 1 because it touches the pin. B and C are the two complicated ones. So at B, we have member 2, and then we have member 3 going away diagonally. I'm thinking of looking at it from over here. And then member 5 is just going away from us. So here's member 3, here's member 5. There's a pin going through all of them. The lowest numbered member at this joint is 2. So I'm going to assume that that pin is part of member 2. Whoops, that's not it. So okay, so at member 2, what we have is 3 and 5 are both in contact with 2, but 3 is only in contact with 2, so there's no force on 3 by 5. And same when you isolate 5, there's no force on 5 by 3. You know, 5 and 3 are just touching those pins. So you'll see that when we go to those free body diagrams. And then C from the side, that's the one I did over there. I guess when I drew it up there, I was sort of thinking of looking at it from the other side, so they're going to be flipped around backwards. But so C, member 1 is going away from us. Member 3 is coming diagonally towards us. Member 4 is going diagonally away from us. There's a pin going through all of them. This is 3 and 4. And you see the same story again. On the lowest numbered member at the joint, there's a force from each other member of that joint. But the ones that aren't the lowest numbered members don't touch each other. Okay, so when you isolate 1 at C, you have a force on 1 by 3 and a force on 1 by 4. But when you isolate 3, you only have a force on 3 by 1. You don't have a force on 3 by 5. Any questions about that? And then D is easy. So all right, so first free body diagram of 1. There's a fixed joint with the wall, so that's an unknown force vector and a couple. And then at the middle, there's a pin joint connecting 1 to 2, so this is the force on 1 by 2. And then at the joint C, you have the force on 1 by 3 and the force on 1 by 4. Now member 2. So that's this short one. Down at joint A, I guess I'm calling that A, so this I'll just leave this as R. That's the only reaction force with the outside. So member 2, at A we have contact with member 1. So this is the force on 2 by 1, or negative force on 1 by 2. And then up at the joint B, if you look at this side view, there's contact with 2 from 3 and from 5. So there's a F2-3 and an F2-5. And then member 3, up at the joint B, member 3 is in contact with member 2, but it's not in contact with member 5. So up here, there's a force on 3 by 2, and I'll write that as negative F2-3. And then down at the joint C, 3 is in contact with 1, but it's not in contact with 4. So we just have the force on 3 by 1, which is negative F13. And then member 4, at the joint C, if you look at the side view, 4 is in contact with 1, but it's not in contact with 3. So we have a force on 4 by 1. And I'll write that as negative force on 1 by 4. And then up at the joint D, we only have 2 bodies in contact here. There's no external forces applied at that pin, so this is just going to be the force on 4 by 5. And what about that distributed load? So it looks like that distributed load is, part of that distributed load is applied at that pin. So why doesn't that show up there? If that is a force applied at that pin, then we're assuming that that pin is part of member 4. So, yeah. That is a good way to think of it, actually. That's not what I was going to say, but yeah, that's a good way to think about it. I was just going to say, remember that these distributed loads are not point forces. So you need some finite, you need that distributed load applied over some finite distance in order to get a finite force. There's only one infinitesimal, amount of that distributed load applied at that pin, and so that doesn't produce any finite force. Okay, so the distributed load itself is applied over member 5, and so that's where it's going to appear. Okay, and then the last one, free body diagram of member 5. So at the joint D, we have the force on 5 by 4. At the joint B, we only have the force on 5 by 2 because 3 and 5 don't touch each other. Yep. What? What places are you thinking of? Mhm. Well, yeah, so this way of drawing it, okay, so on the left end, we have the force on 5 by 4, negative F4, 5. At the joint B, we have the force on 5 by 2, or negative F2, 5. And then we have the distributed load. That's going to act a third of the way from the wall side to the point side. And the total magnitude is, the whole length is 1 meter. You can figure that out from the geometry. And so we have a base of 1 meter times the height of 1,500 divided by 2, so 750. And that's it. Okay, so this might seem like overkill, but let's do this one more time. We're going to renumber everything, and you'll see that those free body diagrams all look different. But if you actually went through the whole calculation with these two approaches, with these renumberings, in the end, if you calculated the external loads on every body, you'd get the same answers. Okay, so it's arbitrary, but once you choose a system, you have to be consistent in that system. Okay, so let me move this. Okay, so do it again, but with a new numbering. Okay, so this time I'll number from this side. So this is member 1, 2, 3, 4, 5. Yes. It's pretty likely that I would ask a question like this because in a 80-minute test, we don't have time to go through like full structures problems unless they're the simplest type, you know. So I do ask questions like this pretty often on tests. So I'm going to start out with drawing the side views of these joints again. I guess, you know, A and D are pretty simple, so I'm just going to do it for B and C. So at the joint B, a side view, now we have the member 5 over there. We have 3 going away diagonally and 2 going away horizontally. And then that's the pin going through everything. And we're going to assume that we're not really assuming that the pin is part of member 2. It doesn't have to be. We're just lumping those two together as a single isolated body. So 2 touches 3 and 5, but 5 and 3 don't touch. And then at the joint C, we have member 4 going away horizontally, member 3 coming towards us diagonally, member 1 going away diagonally, and then the pin, and we're lumping pin in with member 1. So 1 touches 3 and 4, and 3 and 4 don't touch each other. And it works out the same every time. It's the lowest numbered member at that joint touches everything. The ones that aren't the lowest numbered only touch the lowest numbered. That's just how it works out every time. Okay, so member 1. That touches member 2 up at the top. So there's the force on 1 by 2. And at C, it touches 3 and 4. So here's a force on 1 by 3 and a force on 1 by 4. And then member 2 is the one with the distributed load. So we have the downward force of 750 from the distributed load, a third of the way from the left to the right. Then over here we have the force on 2 by 1, so that's negative F12. And then at B, 2 is the lowest numbered member, so it touches 3 and 5. So here we have the force on 2 by 3 and the force on 2 by 5. And then member 3, down at the bottom at joint C, 3 only touches 1, it doesn't touch 4. So we have the force on 3 by 1, or negative F13. And up at B, it only touches 2, it doesn't touch 5. So we have the force on 3 by 2, or negative F23. And then member 4, the wall's a fixed joint. So this is a reaction force and a couple. And then at A, it's in contact with member 5. So that's a force on 4 by 5. And then at C, 4 touches 1, but it doesn't touch 3. So this is the force on 4 by 1, or negative F14. And then the last one is 5. At A, it's touching 4, so that's negative F45. And then the top is joint B. 5 is touching 2, but it's not touching 3. So that's the force on 5 by 2, or negative F25. And the kind of amazing thing about this, I know it takes a lot of time to do this, so, it wouldn't surprise me if you don't find the time to do this. But it's not just that the numbers changed, right? You look at the same member in one of these numberings, and it has a totally different number of forces acting on it than with the other numbering. Like, look at this horizontal member here. It has 3 of these contact force vectors on it, whereas up here it only had 2. So it's not just that you're relabeling things. But if you actually go through the problem both ways, and then add up all the forces that are acting on a member at a single point, and come up with a final representation of all the external loads acting on each member, you get the exact same thing, which is it's sort of hard to imagine how it works out, but it works out. Any questions about that one? Okay, let's do one more, and let's just do the free body diagram again for this one. But this is for number 6. So it looks like this. You have a curved piece like that, and a second piece like this, connected here with a pin joint. And then this second piece is connected to another little piece that's just used to crush something. So, it's in contact with something down there. And the idea is that there's a force P applied here, and we want to calculate, actually the way it's worded more simply than, okay, so there's the joint D, let's call this one A, B, and this is C, where that force P is applied. And the question says, calculate the force applied to the piston at D by the object that's being crushed. Okay. So let's think of this as, so we have this is member 1, this is member 2. And let's think of this as member 3. Okay. And draw free body diagrams of 1, 2, and 3. And let's call the upward force that's applied to the piston. Let's call that R. And that's what we're trying to calculate in terms of P. So I just want you to draw these free body diagrams. I'm going to sign this one over the weekend, so having these free body diagrams will make it easier to work through it. So take a few minutes and see if you can think through that. Yep. No weights. So members 1 and 2, we're used to doing stuff like that. So free body diagram of 1. We have the reaction force here from the pin. I'll call that RA. We have the force here that's applied by member 2, so that's the force on 1 by 2. And then we have this force P. What? Question? That force P is not a variable that we're trying to calculate. That's the parameter that drives this thing. So our answer for our final answer for R is going to have that P in it. You know, like the harder you push down on P, the harder that crushing force is. Okay, so that's free body diagram 1, and you can get Newton's laws using the geometry. Body diagram of 2, same idea. So here we have negative force on 1 by 2. And here we have the force on 2 by 3. Both of these we have geometry for, so this is going to be Newton's second law and the rotational equation. This is going to be Newton's second law and the rotational equation. Okay. But now member 3, up here, there's the force on 3 by 2, so that's negative F23. Then there's a force from the wall. We don't know which direction it goes, but I'll just call it F wall. Assume it's going that way. If we get a negative answer, it doesn't matter. And then we have a force up here that we're trying to calculate. That's R. And the key thing to notice here is we don't have any geometry. We're treating this like it's a particle. We don't know we can't talk about the rotation, the moments, or anything. And so this one is just going to, so this is Newton's second law only. And so now let's think about the equations and variables. We have 3, 6, 3 equations for members 1 and 2, but only 2 useful equations for member 3 because we're not using the moment equation. So we have 8 equations. Okay, and variables, hopefully we have 8. We have RA, F12, F23, and then F wall and R. Okay, so if you ever see a part of a problem where all of a sudden there's no geometry and you try to come up with row vectors and stuff and you're like, there's no geometry given here, probably you're just going to have to treat that like a particle. Okay. Any other questions about that? Yes? Would you have to draw a negative? No, because really what this is we're just, so there's forces coming from both walls, and we're just talking about the sum of those two, and this could come out to be negative 50, and that would just mean it's 50 Any other questions? Okay, you still have time to make it to your 8 o'clock class. So. All right, have a good weekend. See you Tuesday.